Hey Hannah,
Hi,
how are you?
good.
That's
How are
good. How are you
you?
feeling about the final so far?
What was that?
How are you feeling about the final so far?
Not good at all.
Not good at all. Like is it
Uh-uh.
it's just overwhelming towards the end, like with the aldehydes, ketones.
There's so much there's so much material. I just don't know and all of them have the same reagents. It's so
Mhm.
confusing to look at and predict
Right.
what reaction you're doing.
Right. Especially when you look at the exam and then you see a reactant and reagent, it's hard to know what's going on, right? Um, for chapter 17 and 18, they're both gonna talk about aldehydes and ketones, right? But chapter 17 is gonna be more about acidic conditions, whereas chapter 18 is gonna be more about acidic conditions,
Mm-hmm.
right? And for chapter 17, there is a main type of mechanism that you need to know, which is gonna be nucleophilic addition, right? And you have to know these specific functional groups right here. You have to know a hydrate. You would have to know hemi-acetal. You would have to know acetal. You have to know an imine. And for helix class, there's like three fancy imine nomenclature that you have to know, like hydrazone, um, semi-carbazone, and there's one other one, but that's an occult thing. And enamine. So enamine is very similar to an eno, right? Um, all of this here can go back into a carbonyl, specifically an aldehyde or a ketone through a process called hydrolysis, right? And specifically in acidic conditions, hydrolysis will include water and some sort of acid like H2SO4 or H3O plus. Right. So now I'm gonna show you the general mechanism and then we'll dive deep into each of these processes one by one, like hydrate, hem acetal, acetal, imine, enamine, and the reverse mechanism as well. And then
Mm-hmm.
intramolecular reactions mechanisms as well. Okay. And then I'll go over chapter 18 after we go over those reactions here. Okay. Because it will look very similar, right? Let's say, for example, we have this let's say here, this is the hydrate formation. And we're gonna worry about acidic conditions because chapter 15 is mainly about that. Um, let's say we have this carbonyl and we react it with water and acid, H2SO4. Okay. Now, when you're given acid right here, we're gonna activate the carbonyl. Because if you are not given acid, there will be no reaction. This is a weak electrophile. This is a weak nucleophile. We can, however, make this electrophile strong by protonating it with the strong acid. Now, this positively charged oxygen here is very angry. It does not like that positive charge, so it's gonna want to withdraw electrons from that carbonyl carbon, making this carbonyl carbon activated, right? Before it was a small partial positive charge attached to this electronegative oxygen atom, but now it's even more positively charged because this oxygen atom wants to be stabilized by stealing that carbon's electrons, making it more positively charged, right? And now because it's more positively charged, this water here is now able to attack the carbonyl carbon, making a new bond between this oxygen atom and carbonyl carbon and popping the double bond onto the oxygen, leading us to this tetrahedral intermediate here, where we have a neutral OH. and this is the new bond between the carbon that got attacked by this oxygen of the water, which is attached to two hydrogens. And because this oxygen here has three bonds, it will be positively charged. Right. Now to get to the hydrate is a carbon attached to two OH groups. That is what a hydrate is, right? Carbon attached to two OH groups. So we see that we almost have our final answer here. To get to that final answer, we would have to use the conjugate base of the acid that we used at the beginning to deprotonate this positively charged oxygen like that to get us this hydrate here. Okay. Any questions on that mechanism, Hannah?
No.
That's good. So now um the hydrate hydrolysis is the reverse mechanism of this, right? When you see the word hydrolysis, I want you to think of water, right? Um, and specifically, the water in this reaction here will be the carbonyl. So what I mean by that is, let's say you start off with this hydrate, and you want to go back into this carbonyl right here. To do that, you would use water in acidic conditions. And if I were to highlight this oxygen of the water right there, that would be the oxygen of this carbonyl right here, right? To predict the product quickly here, this carbon of the hydrate will be that carbon of the carbonyl, right? Just like how before, this carbon of the carbonyl is that carbon of the hydrate right there,
Hmm.
right? Now, for this first step of the mechanism, we have a strong acid. We're going to do an acid-base reaction. We do not want these alcohol groups anymore, right? Because these will not be there, right? Well, actually, the carbon and oxygen can be one of these alcohols as well. So I'm gonna erase this because the first step here would to protonate one of these alcohol groups to make it into a good leaving group, right? So these 2 points here will be true when you do these mechanisms right here. Keep this in mind. You will protonate the group you want to kick out, right? Because that makes it into a good leaving group. And you will deprotonate the group that you want to keep because that would make it into a bad leaving group. So keeping that in mind, we know currently that this is a bad leaving group, but we want it to leave. So to make it into a good leaving group, we are going to protonate it with the strong acid that we have to give us this oxonium ion here. Okay. Now, once you have this good leaving group right here, a lot of students just kick out the good leaving group by itself, forming a carbocation here. That can happen, but there is something that can drive that leaving group off to make a more stable intermediate, which is to collapse the carbonyl down, make a double bond here between this carbon and oxygen nearby. That would break the octet rule for this carbon. So we would have to kick off that good leaving group that we formed to give us this intermediate and water side product that left right there. And then the last step of the mechanism would be to deprotonate that positively charged oxygen to give us this neutral carbonyl here. And that's the reverse mechanism right there, right? We saw that we wanted to make this into a good leaving group. So we protonated it to make it positively charged, and then it is a good leaving group, right? In this example right here, this is a good leaving group, but if we wanted it to keep it for the hydrate, we had to deprotonate it with the conjugate base, okay, to make it into a bad leaving group. Any questions on this mechanism? Hannah?
No.
Okay, that's good. Now, before we get into hemiacetal, I want to show you what the hemiacetal is. It's half of an acetal where we have an OR group and an OH group on the same carbon, right? Um, you can have this hemiacetal right here, or you can have this hemiacetal right here. And I'm going to color code the hemiacetal carbon in blue, which is going to be this carbon for this structure and this carbon for this structure. The one on the left is going to be considered unstable And because it is unstable in lab, it would be hard to isolate, meaning that it's hard to keep in a container. Whereas the one on the right will be the stable hemiacetal in the ring structure, which is going to be easy to isolate, easy to maintain in a container.
So Helix said that
Uh-huh.
we're like unlikely to get a hemiacetal and predict the product and like
Uh-huh.
hydrate.
Yeah.
Do you know if like we would like if that just means for the unstable one?
Hmm. Right. For the unstable one here, if you were in acidic conditions, you would then go all the way to an acetal, right? And this hemiacetal here will tend to be considered an intermediate in the mechanism, which will eventually lead you to the acetal, which is a carbon attached to two OR groups, like that,
Mm-hmm.
right? So because you mentioned that, I'm going to show you how to pick the product quickly if you were given a carbonyl and you're given some sort of alcohol in acidic conditions. This is the carbonyl carbon in red. That red carbon right there will be attached to two OR groups, and the OR groups will come from two equivalents of the alcohol we have here. Because I use ethanol here, the OR groups would be two OR groups that are like that, ethoxy groups like that. If I use
Mm-hmm.
propyl, it would be like propyl group like that, right? And this carbonyl here would leave in the form of water, like that, right? Now you can also do the reverse mechanism of this, which would be hydrolysis of acetal. So if you wanted to go back into the carbonyl, right, where this carbon here is the same carbon right there, you would do hydrolysis, which includes water and acid. And specifically, the water oxygen here will be the oxygen of the carbonyl, like that. And then in the mechanism, you'll kick out two alcohols which will come from these two OR groups here, like that.
Mm-hmm.
Right. Now, um, there is one example where you could form a acetal, a hemiacetal, but it has to be cyclic in this form right here, right? And that is intramolecularly, right? So we'll label this intramolecular hemiacetal formation, right? Because if you do like some practice problems, you can't come across this here. Right, and I'll give you a simple one to start off with. Okay, and then acidic conditions, H2SO4. Now, without the H2SO4, there will be no reaction because we have a weak electrophile here and a weak nucleophile here. Because of the acid here, we're going to activate one of them, specifically the electrophile, to make it more positively charged, like that. Similar thing as we did previously with the previous mechanism. Okay, now because we have an activated electrophile, which is this dot right here, and we have this alcohol, which will be our nucleophile, this nucleophile would attack that electrophile, pop the double bond onto the oxygen, and because we have our nucleophile on the same molecule as our electrophile, this is considered an intramolecular reaction where we will form a ring because all intramolecular reactions will form a ring, and the way that I predict the product quickly here is I highlight from the nucleophile atom to the electrophile atom, and that would be the ring backbone. So I know that my ring will be one, two, three, four, five atoms long. And one of the atoms in the ring is this oxygen atom right there. So we know that our base template of the product here will be this five-membered ring where oxygen is one of the atoms here. Where I know because the way I numbered it, oxygen would be number one. And then you can number this two, three, four, five. The order doesn't matter here, but just to be consistent with where things are. The oxygen one still has a proton attached to it. Um, three right here will have a methyl attached to it. Four will have an ethyl attached to it, and five will have a hydrogen attached to it, but I'm going to leave it as invisible implied now. It could be a isopropyl group, and you would just have to draw the isopropyl group out like that. And it no longer is double bonded to this oxygen, but it now has a single bond OH like that. That's neutral. And then the last step of the mechanism here would be to just deprotonate this positively charged oxygen to give us this final product here, which is going to be our hemiacetal, because this carbon right here has an OH group and OR group. And this is when we could stop at this hemiacetal point right here.
So we could get that and predict the product, right?
Yes, you can get this for predictive products, especially when you look at like Levens practice sheets. You will see this as the answer for some of the practice reactions. You will end with the hemiacetal that is cyclic. You do it intramolecularly, right? If you were to do it intermolecularly, where the carbonyl and alcohol are separate from each other, they're not in the same molecule like this, then you don't stop at the hemiacetal. You go all the way to the acetal right there, right? Because from here, the intermediate would be the hemiacetal. We have an OH group there and an OR group there. But then you don't stop at the hemiacetal. You keep going until you reach the acetal in this form because this hemiacetal is not in a ring. It's not stable. Right. Okay. Um, Now we talked about hemiacetal formation, hemiacetal hydrolysis. Um, we could also do hydrolysis of this hemiacetal, but it doesn't have to be that specific one. It could be different. It could be like instead of a five-membered ring, it could be a six-membered ring like this. And then we can have some random groups like this, right? And then if you react it with water and H2SO4, we're gonna get a carbonyl back. Now in the mechanism, right? What did this carbonyl oxygen become, right? If we track it all throughout, what did it become in the product?
The alcohol.
Correct. So when you have a hemiacetal like this, know that the alcohol was a carbonyl. And this right here is the hemiacetal carbon because it is attached to an OH group and an OR group. That hemiacetal carbon was a carbonyl carbon before. So we could cut that bond right there because we know that this alcohol was a carbonyl here, and this oxygen here was an alcohol before, right? Because if you track the alcohol in the mechanism, alcohol, alcohol, right? That alcohol oxygen is part of the ring. So if we go backwards here, this is what you would get. And we have an aldehyde here because we have an invisible hydrogen here. If we had a methyl group there, then that would be a methyl group, a ketone. But in this case, we have an aldehyde, like that. Okay. Any questions on this, Hannah? Like this is just
Mm,
predicting the product, not the mechanism.
yeah, no
Okay,
questions.
that's good. Now we're gonna go straight into imine, right? So I'm gonna give you the ingredients to create the imine, which is a carbon double bond nitrogen, right? And this nitrogen to be neutral has to have three bonds, so it could be bonded to a hydrogen, or it could be bonded to an R group, like that, right? So the ingredients for an imine would be ammonia or a primary amine reacting with a ketone or aldehyde, which is the unit that we're in right now, or aldehyde, in acidic conditions. So the acidic conditions here, the proton source can be sulfuric acid, H3O plus, or HCl. So a simple example here is if we have this carbonyl here, and the reason why I wrote it like this is because I don't want you to get confused on the exam when you see, like, let's say, for example, this, right? And then this tends to work in mild acidic conditions, so pH of around 4 to 5, versus this. So you see that, and you see this right here, right? Like, because they are formatted differently does not mean that there are different reactions. They are the exact same reactions. It's like saying, this is A, this is B, so A plus B will give you C. This is B, right? This is A. B plus A is also C, like that.
Hmm.
Just formatted differently. right? These would be the ingredients for this imine formation here. You would have ammonia, a primary amine, a, reacting with a ketone or aldehyde in acidic conditions. That would give you an imine, which is a carbon double bond nitrogen, like that, right? Now to predict the product quickly here, this carbonyl carbon would be in red. That's going to be the imine carbon. So we have a carbon double bond nitrogen attached to this R group here. Because in the mechanism, two hydrogens will go away. Two hydrogens will go away in the mechanism. So that would be the final product right there, right? So that would be the exact same thing as this right here,
Mm-hmm.
right? Okay. Now, I want you to describe to me what the mechanism is going to be step by step, right? It's very similar to what we did earlier, with all the nucleophilic addition mechanisms. In slightly acidic conditions, what is going to get protonated to activate this reaction to go through?
The oxygen will get protonated.
Mhm. Correct? Make that into a strong electrophile. Now, once it's a strong electrophile, what can attack this strong electrophile here?
Um, the nitrogen.
Correct, of the amine, making a new bond between the nitrogen and carbon, popping that double bond onto the oxygen, giving us this tetrahedral intermediate here where we have a neutral alcohol. This is the new bond between the carbon attacked by this nitrogen here. This nitrogen right here is this nitrogen right here, and that nitrogen is attached to this R group and two hydrogens. And because that nitrogen has four bonds, it's positively charged, right? Now, we have something called a tetrahedral intermediate here, where we have a good leaving group on this group and a bad leaving group on this group right here, right? But we see on the product we want an imine, a carbon double bond nitrogen. So we want to keep this group. We want to kick out this group, right? So in the mechanism, you could do it at the same time here. You would want to make this into a bad leaving group by deprotonating it and make it neutral. And you would make this into a good leaving group by protonating it and making it positively charged. So we can do that at the same time by protonating this group and deprotonating this group at the same time like that, which would give us this desired tetrahedral intermediate where we reverse the roles here. This is now the bad leaving group, which is good because we want to keep that group. This is now the good leaving group, which is good because we want to kick that out. Now, like we said earlier, we don't just want to kick it out by itself like that and form a carbocation, right? The driving force that would do that is to create a double bond nearby with this species, making a carbon double bond nitrogen and forcing that water to leave as a leaving group, H2O, and form this iminium ion. And it's an ion because it has a formal charge of +1. And it's an iminium ion because we have a carbon double bond nitrogen, where the final thing here is to use a base. You can use the second equivalent of the amine to act as the base, serve as the base, to deprotonate and neutralize this positively charged nitrogen to give us this neutral imine here, like that. Okay.
Mm-hmm.
Any questions on this one, Hannah?
No.
Okay, that's good. Now I want you to describe to me the mechanism for imine hydrolysis. Right. So when you see hydrolysis, what reagents do you think of here?
Water and acid.
Water and acid, correct? And with this unit here, what is the imine going to get converted into? Like what will this iminium imine carbon here be converted into with water and acid?
A carbonyl.
Correct. And the carbonyl oxygen will come from the water. So that blue oxygen in the water, it will be this blue oxygen of the carbonyl, and the leaving of that leaves will be this neutral ethanamine there. Okay. Now, what do you think is going H2SO4? Yeah. Well, H2SO4. Okay. What do you think is going to happen in acidic conditions here?
The nitrogen gets protonated.
Uh-huh. Correct. Convert that into a strong electrophile, specifically the imine carbon. There is no hydrogens there because if there was a hydrogen there, that nitrogen would be positively charged. We get that hydrogen there by protonating it, making this nitrogen positively charged, which makes this iminium carbon a stronger electrophile, which what would happen next here?
Um, the oxygen in the water would attack that
Uh-huh.
carbon.
Correct. Pop the double bond onto the oxygen and give us this here. Okay, now what will happen next once we have this tetrahedral intermediate?
Um, you kick off the oh, you want to make the nitrogen a good leaving group and the oxygen a bad leaving group.
Correct. We want to reverse the roles here, and we could do that at the same time by deprotonating this group to make it into a bad leaving group, and protonating this group, making that into a good leaving group at the same time with those arrows, reversing the roles here, which will give us this tetrahedral intermediate. And then what is the driving force to kick off this good leaving group that we formed here?
The then it'll do it intramolecularly, right?
Uh-huh. Correct. Well, we would form a double bond with this oxygen nearby,
Yeah.
and this would break the octet rule of this carbon because this carbon would then have one, two, three, four, five bonds. To conserve the octet rule, we have to kick out that good leaving group that we formed right there, like that, forming this ethanamine side product, and this carbonyl with a positive charge like that. And from here, we can then deprotonate this positively charged oxygen using that conjugate base to get this neutral carbonyl here, like that, right? And
Mm-hmm.
that's hydrolysis of imine right there. Now let's talk about enamine, right? Um, it doesn't have to be intermolecular. You know how I did it intermolecularly, like forming an imine where the carbonyl and primary amine were separate from each other.
Mm-hmm.
We could have also done this intramolecularly, right? Where the carbonyl and amine are in the same molecule. So let's say this is one, two, three, four, and let's say this is five, NH2, and then we have this methyl ethyl in slightly acidic conditions with the pH of around 4 to 5. Um, we already know the mechanism, right? But this time it's going to be intermolecular, where this is going to be the electrophile, this is going to be the nucleophile. And I'm going to show you how to predict the product quickly here. I'm going to number one my nucleophile atom, and then I'm going to go until I hit my electrophilic atom, knowing that I would make a five-membered ring, where specifically one of the atoms of this five-membered ring here would be nitrogen. So I'm going to draw that template out like this, right? Where this is going to be one, this is going to be two, three, four, five. And this right here will be the new bond between one and five. And because I know this is a primary amine, I'm making an imine, right? Which is a carbon double bond nitrogen. And the carbon double bond nitrogen would be between 1 and 5 right here, right? Between
Mm-hmm.
the nucleophile and the electrophile. And I know that this carbonyl of 5 right here would no longer be there because in the mechanism it leaves as water, right?
Mm-hmm.
But 5 is attached to this isopropyl, so we are going to attach the isopropyl there like that. 4 is attached to an ethyl group, 3 is attached to a methyl group, and 2 is attached to two hydrogens. So this is our final product here, which is a neutral amine here, where we get rid of these two protons in the mechanism as well. To have this neutral nitrogen atom with three bonds, one, two, three, like that, right? Now, if you were given this as the reactant in the question instead, and you're given acid and water, you know that you're doing hydrolysis to get back to the carbonyl. And to predict the product quickly here, know that this imine carbon right here, the carbon double bond nitrogen, is the carbonyl carbon. So you could cut that bond in half and show that that red circled carbon there was the carbonyl. And then everything else you could draw in that similar format, like ozonolysis. And then this right here, you add in two hydrogens, two protons to this nitrogen, like that. And that would give you the same exact structure as this here,
Mm-hmm.
right? So that's going hydrolysis. That's going backwards from a cyclic amine to the ingredients that we need to form an amine. A carbonyl, like a ketone or aldehyde, plus a primary amine or ammonia in acidic conditions here. Okay, nice. Let's now talk about enamine. Enamine formation. Okay, so for enamine formation here, an enamine is similar to an enol. An enol was an alkene next to an alcohol. An amine would be an alkene next to an amine. But this amine here will have no protons. It will be a tertiary amine when we form this right here, right? We have an alkene next to this tertiary amine right here. So that will give you a clue of what the reagents will be. We will have a secondary amine, right? So it could be like this, where the two arguments are different with one proton, plus a ketone or an aldehyde, plus a proton source, like around a pH of 4 to 5, and that would give you the enamine. These three ingredients will give you the enamine, right? Now, if you want to go back to these three reagents here, you do hydrolysis with acid and water. Okay. Now, let's talk about an example here. Let's say, for example, we have this simple ketone reacting with this um, secondary amine here. I'm going to show you how to predict the product quickly, right? Uh, we know that we have our three ingredients for enamine formation, a ketone or aldehyde, a secondary amine, and a pH of 4 to 5 acidic conditions. This carbonyl carbon here is in red. That's going to be the enamine carbon attached to this amine, this nitrogen here. The proton would no longer be there, attached to its two R groups. One, two. And we put a double bond right there next to the amine. So that would be the product right there, our enamine. Okay. Um, Now from here, let's talk about the mechanism, which is going to be a little bit different at the end of what we're used to. The first step will always be the same. Activate the electrophile by protonating it with the acid here to give us this intermediate. And now once we have this right here, this neutral amine that is not a primary amine, because a primary amine would lead to a amine, right? The secondary amine here will attack this carbonyl carbon, pop the double bond onto the oxygen, and give us this tetrahedral intermediate here. New bond, nitrogen, boom, boom, hydrogen, positive charge. Where we want to keep this group here, we want to kick out this group here. So we got to reverse the roles here. We got to make this into a bad leaving group by deprotonating it. We have to make this into a good leaving group by protonating it. And we can do that in the same step like this. We deprotonate this group while protonating this group at the same time, leading us to this desired tetrahedral intermediate right here. Now, once we have this desired tetrahedral intermediate, we could drive the good leaving group off by making a double bond between this carbon and nitrogen, kicking out this good leaving group that we just formed right here, to give us this intermediate where water is a side product that left. This is a carbon double bond nitrogen that we formed right here. This nitrogen with 4 bonds will be positively charged. Now, we cannot neutralize this positively charged nitrogen by deprotonating it, right? Because there are no protons on this nitrogen, so that's why we cannot do that. We still can, however, neutralize it by elimination. So think of it like E1, E2 type reaction, where this is going to be the alpha carbon, the first carbon away from the iminium ion, right? This is the alpha proton right here. So some sort of base, we could use a second equivalent of the neutral amine that we have to serve as the base here to grab that alpha proton, make a double bond there, pop the double bond onto the nitrogen. So this is like E2 type reaction, right? Where this is the base, we grab the hydrogen here, make a double bond there, and then like in quotation marks, kick out the good leaving group. But this
Hmm.
group does not leave entirely because it's double bonded. Only one of the bonds goes onto the nitrogen to give us this enamine here, an alkene next to an amine there, like that,
Hmm.
right? That's good. So that's why at the end it's a little bit weird because at the end we don't neutralize this positively charged nitrogen by deprotonating it. We neutralize it by doing an elimination reaction to create this alkene and neutral amine here. Okay.
Hmm.
Nice. Now let's talk about hydrolysis of um, enamine. So let's say we have this enamine here, and we want to go backwards into this carbonyl with acid and water. Um, the mechanism would be like this. So this will go into chapter 18 now. The nucleophile is not this nitrogen atom. The nucleophile is this alpha carbon right here, right? And the reason why is because if you think about the resonance structure here, which we could go do by drawing those arrows, right, where the nitrogen pair of electrons goes down to make a double bond right there and give a pair of electrons on that carbon right there, we see that there will be a negative charge on this alpha carbon, making that the nucleophile, right? Um, like if you compare the negative charge of this carbon versus the pair of electrons on this nitrogen here, this is less stable, right? Because it's on a non-electronegative carbon atom, and because it's less
Mhm.
stable, it's the more reactive nucleophile,
Mhm.
right? Or base. So in this case right here, that's going to be acting as the base in the first step, where we go down to form the iminium ion. And then we know that this alpha carbon as star right here will act as a base to grab that proton from the acid and give us this iminium ion intermediate here, where we have a carbon double bond nitrogen with a positive charge there. And then there is a new proton here, which comes from the strong acid, but we're going to leave that as invisible. It is there, but we're going to leave that as invisible. Right. And then water here will then attack this iminium ion electrophile, pop the double bond to oxygen, and get back to this tetrahedral intermediate here, where we do the same proton transfer steps, right? We deprotonate the group that we want to keep, we protonate the group we want to kick out. Because we want to go back to the carbonyl here, we want to kick out this group, we want to keep this group to get to the carbonyl. So we got to reverse the roles here by deprotonating the group that we want to keep and protonating the group that we want to kick out at the same time, which will give us these intermediates here, right? So instead of like trying to memorize each mechanism step by step, you could like think of it as like a story like this, like why it forms like this, or you can just put it in your note card. Have you made your note card yet, Hannah?
Yeah, I made my note card.
That's good. That's good. That's good. Is this in the note card here too?
Yeah,
Yeah, that's good. That's good. How long did it take you to make that note card?
pretty long.
I know, like it takes hours to include every single thing, final thing,
Yeah.
right? Like that's good that you got it now, so that you don't last minute cram it and be stressed about it.
Mhm.
That's good. Okay. And then we have this secondary amine here. That is neutral that left. And then the last thing here is like we could use the conjugate base of the strong acid that we formed in the first step to deprotonate and neutralize that positively charged carbonyl to get this neutral carbonyl here, like that.
Mhm.
Okay. Now, those are the main reactions for chapter 17. There are other reactions as well as like deoxygenation, like carbonyl deoxygenation by Clemmensen reduction, Ruff-Kishner. There's Wittig reaction, Baeyer-Villiger reaction as well. But what I want to do is I want to go over the big three chapter 18 reactions, right? Which are aldol, condensation, or dehydration if you're
Mhm.
heat. Um, micro addition, which is a type of 1,4 addition, right? Which is a type of 1,4 addition, and then Robinson annulation, which is the last reaction you learned in 118B. Okay. Now, I will give you a chart of the differences between these right here because all of these here use the exact same nucleophile. That's why it looks very similar for these
Yeah.
three specifically, right? And like we said, this is going to be chapter 18, the big three reactions. And we said earlier that chapter 18 will work with basic conditions. Okay. Let's talk about aldol condensation first, or dehydration. Okay. Condensation would be if you were given low temp like 0 degrees Celsius. Dehydration would be if you're given heat like that. And you have to have at least two alpha protons. And show you why. Because even if you do have heat, but you only have one alpha proton for the nucleophile, you can't do dehydration. You're stuck with condensation.
Mhm.
And there's three different types of aldol here. There's a mixed aldol condensation. There's a cross, yeah, mixed or crossed, I mean. That's the second type I want to go over. Mixed or crossed aldol condensation. The first step is going to be self aldol, and the third one is going to be intramolecular aldol. Right. So let's talk about self aldol first. Well, before we talk about that, all of this here, right, will follow these rules. The nucleophile for aldol is going to be an enolate ion, which will look something like this, where we have a deprotonated enol. So you know how an enol is an alkene next to an alcohol like that? When you deprotonate this enol, you get something called an enolate ion, where you have a negative charge on the oxygen like that. But this negatively charged oxygen here is not the nucleophile, right? Because we know that when we do resonance, we can form a carbonyl here and give a carbon, this alpha carbon here specifically, a negative charge. And the negative charge on this alpha carbon here is less stable than the negative charge on the oxygen. And because it's less stable, it's going to be more reactive, more nucleophilic. So on this enolate ion here, the nucleophile is this alpha carbon, not this O minus right here.
Mm-hmm.
Right? The electrophile for aldol condensation is going to be the carbonyl carbon of an aldehyde, right? Or it could be a ketone if you do it intramolecularly. Intramolecular, right? Now this is gonna talk about what's more reactive, a ketone or an aldehyde, like what carbonyl carbon has a bigger positive charge, right? So if you were to compare, like let's say this aldehyde versus this ketone here, the aldehyde carbonyl carbon would be more electrophilic with a bigger positive charge because it only has one R group, and like we said in the benzene unit, an R group is an EDG. It will donate electrons towards the system. Whereas a ketone has two R groups donating electrons to the carbonyl, making it more neutral, more stable, more less positively charged. Whereas aldehyde only has one R group, making it like not as neutral. Right? This hydrogen here is not an EDG.
Mm-hmm.
Um, so that's why aldehydes are more electrophilic, more reactive than ketones. The product of aldol condensation here, right, is going to be something called an aldol or a beta hydroxy carbonyl, which looks something like this. If you have a carbonyl, right, beta to that carbonyl, you will have a hydroxy group. Like let's say this is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. At the beta carbon, you have a hydroxy group. So that's why we call this a beta hydroxy carbonyl or an aldol, right? Where you have an aldehyde, this tends to be an aldehyde, and an alcohol. But
Mm-hmm.
know that the alcohol and aldehyde or carbonyl here are not right next to each other. They're separated by one carbon, the alpha carbon right there,
Mm-hmm.
right? That's condensation product right there. Condensation. If you're able to do dehydration with heat, you're going to make a double bond between the alpha and beta carbon and get rid of the alcohol on the beta carbon, right? So there will be no more alcohol on the beta carbon, but there will be a double bond between the alpha and beta carbon, which because there is an unsaturation or double bond between the alpha and beta carbon, we call this an alpha beta unsaturated because there's an unsaturation between the alpha and beta carbon, alpha beta unsaturated carbonyl, like that.
Mm-hmm.
Okay. Um, and that's with dehydration right there, which is the aldol dehydration product. Okay. So all of this will be true for all types of aldol, self-mixed or intermolecular. So let's look at an example of a self one. If I were to give you this aldehyde here in basic conditions like NaOH, water, and heat here, here's the mechanism. You're given a very strong base, hydroxide ion. This very strong base here is going to look for the most acidic proton. The most acidic proton here in this molecule is the alpha proton. If this is the carbonyl carbon, this is the alpha carbon, which is the first carbon attached to the carbonyl carbon, making this the alpha proton because it's attached to the alpha carbon. So this strong base here is going to grab that proton right there and generate our enolate ion. We make a double bond here and pop the double bond to the oxygen to give us this enolate ion here. But we know that the nucleophile would not be this negatively charged oxygen. The nucleophile would be this asterisk or starred alpha carbon there of the enolate. This is when we bring in a second equivalent of the aldehyde to serve as our electrophile, which is going to be this dot carbonyl carbon there. So when we reform the carbonyl here, we know that this alpha carbon here is going to go attack this dot carbon and pop the double bond onto oxygen. And that's able to happen because when we reform the carbonyl here, this double bond has to go onto that carbon, giving that carbon a negative charge, whereas that negative charge can just like go and attack that electrophile and pop the double bond onto oxygen right there, making a bond between the star and dot, making a bond between the nucleophile atom and electrophile atom right there. And this is when we like keep track of the atoms by starring and dotting the atoms here, right? Because if you look here, this is the starred molecule with the starred atom here. There will be a new bond between the star and dot. That's the new bond from the attack right there. The dot atom here has an ethyl group, so I'm going to draw that ethyl group out like that. A hydrogen, which I'm going to leave as invisible implied. It is still there, but I'm going to leave it as invisible. It was double bonded to an oxygen, but it is now single bonded to an O minus because we popped the double bond onto the oxygen like that. Where because we're given these conditions here, the most protic solvent we have is water, which will serve as our proton source. So we'll use water here to protonate this O minus to become a neutral OH like that. Now, if you're given 0 degrees Celsius, you stop here because this is your aldol condensation product, which is beta hydroxycarbonyl. You have an aldehyde and you have an alcohol here, aldol here. But because we're given heat, we're gonna keep going to do aldol dehydration, right? So another base here will come in and look for the most acidic proton, which will be this alpha proton in between the carbonyl and alcohol to generate the enolate ion again, like that. When we do that, we're gonna form water. We're gonna have this enolate ion. And now, once we have that, we could reform the carbonyl, shift this double bond over here to make a double bond between the alpha and beta carbon, right? Because this is the alpha carbon, this is the beta carbon. We're making a double bond or unsaturation between the alpha and beta carbon, and then kicking out this OH leaving group here. Now, we said earlier that OH is a bad leaving group, but in aldol condensation or dehydration specifically, this is the first time we're seeing it able to leave in basic conditions. And this is the only irreversible step of the mechanism here, where we form this alpha beta unsaturated carbonyl, like that. Right? Because we have a saturation between the alpha and beta carbon like that. Okay. Any questions on this, Hannah?
No.
Okay, that's good. I'm going to show you how to predict the product quickly if this was shown to predict the product without doing this entire mechanism to save you time. If you're given an aldehyde like that, and then you're given basic conditions like NaOH, water, and heat, we know that we're going to do aldol dehydration here because basic conditions will generate our nucleophile, the enolate ion, and then we have excess amount of this. This could be our electrophile. So star, the alpha carbon, that can be the nucleophile. We know that this alpha carbon here has the ability to become an enolate ion because it has an alpha proton. If this has no alpha proton, like let's say for example, there were like three R groups there and there's no protons here, this can never be the nucleophile for aldol condensation or dehydration. Because we said earlier, the nucleophile for aldol condensation or dehydration is an enolate ion. And to form that enolate ion there, we need a proton on the alpha carbon to deprotonate and generate that enolate ion. But if there's no alpha proton, this cannot be the nucleophile. It can, however, be the electrophile, right? But we're going to talk about that in the crust or mixed aldol. So we're going to start this alpha carbon here that has at least two alpha protons, right, for aldol dehydration. Um, but it has only needs one alpha proton to do aldol condensation to make the enolate ion. We bring in a second equivalent of the aldehyde, carbonyl, to act as our electrophile. To predict the product quickly here, copy and paste the starred molecule as is, right? Make a new bond between the star and dot. The dot has an ethyl group and a hydrogen. I'm leaving the hydrogen invisible. The carbonyl is an OH. So if you're given 0 degrees Celsius, this is where you stop. But because we're given heat here, get rid of the OH, and put a double bond between the star and dot to get your final product like that.
Mm-hmm.
Right. Now, the reason why I said for auto dehydration, you need heat and at least two alpha protons is because let's say, for example, you only have one alpha proton where you use this instead, right? Where you use, um, uh, where is it? Where you have this right here. You cannot do auto dehydration even if you have heat because this carbon breaks the octet rule. It will have five bonds. One, two, three, four, five. Right? But if you have two alpha protons, the first one is used to make the enolate ion. The second one is used to make this alpha beta unsaturated carbonyl, like that. Okay? That's how you predict the product quickly without a dehydration or condensation. There.
Mm-hmm.
Okay, nice. Now, for synthesis, I'm going to show you how to break it apart to predict what your reactants were. Let's say you were given a um, random alpha beta unsaturated carbonyl like this, where if this is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. The first thing you would do to predict the reactants here is locate the alpha and beta carbon. So we did that already. This is the alpha carbon, this is the beta carbon. Then you make a cut between the alpha and beta carbon. The alpha carbon would be the star, the beta carbon would be the dot. So the star, like we know, will be unchanged. This is our nucleophilic molecule here. The dot had a carbonyl. So this dot here with the beta carbon has an isopropyl group, and that was a carbonyl there. And because we have a hydrogen here, that hydrogen I'm going to draw out to show that that is another aldehyde. So we did aldol dehydration with these reactants here, where we had a star and dot in basic conditions to form the enolate ion, NaOH, water, and because we have aldol dehydration, we have heat. So that's how you can go backwards retrosynthetically if you're given this alpha beta unsaturated carbonyl, how to predict what reactants were used in basic conditions with heat to create this aldol dehydration product there. This is the nucleophile, this is the electrophile.
Mm-hmm.
Right? And this is specifically mixed or crossed aldol because we see that we are using different aldehydes or ketones, right? Um, to do this aldol dehydration product. Nice, nice. Okay, that's good. Now we're gonna dive deeper into the mixed or aldol type. Mixed mixed or crossed type, mixed or crossed aldol type. Okay, so let's say we have something like this reacting with base, water, and heat. How would you predict the product quickly here? What is your nucleophile? What is your electrophile?
There's no alpha hydrogen on the one with the benzene.
So because there's no alpha hydrogen here, can this be the nucleophile?
No.
Yep, cannot be the nucleophile. It can, however, be the electrophile because it is a carbonyl carbon of an aldehyde, like that,
Yeah.
right? Now, to make this more high yield, the nucleophile here does not have to be an aldehyde. It can come from a ketone like that, right? And what's more likely to become an electrophile? The aldehyde carbonyl carbon or the ketone carbonyl carbon? Like, what is more reactive, aldehyde or ketone?
Um, the aldehyde, right?
Yeah, correct. Because it has a bigger positive charge, since it only has one R group donating electrons to it,
Mm-hmm.
whereas the ketone has two R groups donating electrons to it. So it makes more sense for this aldehyde to be the electrophile and this ketone to be the nucleophile, because one of the alpha carbons here has at least one alpha proton to go through. And can it do dehydration or is it stuck at condensation, even with heat?
I don't know.
So for dehydration, right? Um, we need at least two alpha protons on the nucleophile. So if we have the nucleophile here, we had at least two alpha protons. So that's good for aldol dehydration product like this. If there was only one alpha proton, right, where there's only like one alpha proton here, that is not good for dehydration because we cannot make this double bond right there between the alpha and beta carbon. That would break the octet rule.
Mm-hmm.
Right. So if your alpha carbon of the nucleophile has at least two alpha protons, you could do auto dehydration, right? Which is what we also summarized here. For auto dehydration, you need heat and at least two alpha protons on the nucleophile, right? Which is the enolate ion. Okay. And in this case, we do have at least two alpha protons. We have three, right? So we can do auto dehydration here. How would you predict the product quickly here without doing the mechanism? If this is your nucleophile and this is your electrophile here.
Um, I would copy the one with the nucleophile, and then I would attach it to the dot carbon, and then I would attach the alcohol and then the benzene.
Uh-huh. And the hydrogen we can keep invisible. Now, this right here is going to be our outer condensation product, which is a beta hydroxycarbonyl. Do we stop here or do we keep going based on the conditions?
Um, no, you can keep going because the heat. So you can have the double bond between the star and the dot and no alcohol.
Mhm. Correct, correct. And in this case here, does it break any octet rule? It doesn't, right? Because this right here had a proton for us to donate in the mechanism. If, however, like let's say we had only one alpha proton, like we had the isopropyl group here, um, right? Well, no, this is not an aldehyde. This is supposed to be a ketone. Okay, isopropyl group and then isopropyl group like that. Um, right. Let's see here. Say isopropyl group, sorry, carbon, isopropyl group like that. This would not be able to form because it breaks the octet rule. This carbon has five bonds. One, two, three, four, five. So sometimes even if you have heat, you can't get the auto dehydration product because it would break the octet rule like that.
Mm-hmm.
Right? In this case, we don't have to worry about that. It won't break the octet rule. Okay? Nice, nice. That's how you can predict the product quickly for auto dehydration to get this alpha beta unsaturated carbonyl. Okay? Now let's talk about intramolecular aldol dehydration, where the nucleophile and electrophile will be on the same molecule. So let's say, for example, we have something like this. And we don't have to have an aldehyde here. It can be ketone now because we said earlier that the electrophile, it's usually a carbon-to-carbon of an aldehyde, but if it's intramolecular, the aldehyde or the ketone can be the electrophile as well. Okay. And now that would make things more tricky because we're given two ketones here, and if we're given NaOH, water, and heat, we have to figure out what's our star, what's our dot, right? And I'm going to show you how to predict the product quickly here. What was our nucleophile again, Hannah, for this mechanism?
Um, I don't know.
So the nucleophile for aldol condensation or dehydration is the enolate ion, right?
Yeah.
Um, and that this is the enolate ion here. And what can we do to create the enolate ion from, let's say, this ketone here? Like, what can we do if we're given basic conditions? What are we looking for in the
The alpha hydrogen.
Huh? Correct, the alpha hydrogen. So there are three, or there's, I mean, there's multiple, right? There's multiple different potential alpha carbons here, but at least one alpha hydrogen, right? How many do you see? How many potential alpha carbons do you see that has at least one alpha proton?
Um, three.
Mhm. Correct. One here, another one here, and another one here. This here is an alpha carbon, but this alpha carbon cannot be the nucleophile because there are no alpha protons there. So we cannot deprotonate that alpha carbon right there. So these are our three potential nucleophiles, right? What was the electrophile again for aldol condensation or dehydration, Hannah?
What was the what?
The electrophile.
Oh, the carbonyl
Uh-huh.
carbon.
Correct. And in this case, we see two of them, one and two. We want to choose the best combination that will give us the most stable ring. right? So let's say for the nucleophile stars, I label them A, B, C, and the electrophile, I number them 1, 2. What nucleophile A, B, or C will react with what electrophile 1 or 2 to form the most stable ring here,
Mm,
right? And think of the
B.
most B, carbon B, right? So if we use carbon B as the nucleophile right here, that
Mhm.
means it will react with either this electrophile, and it cannot because like we can't make a two-membered ring, that's impossible, or react with this electrophile. If we react with this electrophile, that would make a one, two, three-membered ring, which is like that. Right. And we know that this three-membered ring is unstable because there's a lot of ring strain right there, right? For stable rings, look for 5 to 6 membered rings. 5 to 6 membered rings, right? So it wouldn't be B because B would make a three-membered ring at most, which is not good. Okay. A would do the same. It can make a two-membered ring. It can make a three-membered ring, but it won't be as stable. But let's look at C here, right? So let's erase these two because we know that those are gonna make unstable rings. But if we look at C right here and say that this is the nucleophile, we don't want this to be the electrophile because we cannot make a two-membered ring. That's impossible. But we can say this is the electrophile here to form a one, two, three, four, five-membered ring, and that's one of the stable rings right there. So this would be the backbone of the five-membered ring right here. So I draw that backbone out, which is a five-membered ring like that. And we could number it like one, two, three, four, five there. Where one is the star, five is the dot. There's a new bond between one and five right there. Five right here will have the alcohol, and we'll see if we can get rid of that later. It also has a tert butyl, so draw a tert butyl coming out of five like this. Four has a methyl group, two has a carbonyl, one has an ethyl, right? Where this is the alpha carbon, this is the beta carbon. And because we have heat here, we can get rid of the alcohol and put a double bond between the star and dot, between the alpha and beta carbon to get this aldol dehydration product, which is a cyclic alpha beta unsaturated carbonyl, like that, right? So the tricky part here about this mechanism is figuring out what's the best nucleophile and best electrophile combination to lead to a more stable ring structure, like a 5 to 6 membered ring structure, right? This couldn't be the nucleophile because that would have made a three-membered ring at best. Uh, this could be the nucleophile because that would make a three-membered ring as best. So the best nucleophile we use here is this because that made a one, two, three, four, five-membered ring. And this right here would have to be the electrophile, not this right here. Because if we chose this as electrophile, like there will be no reaction, right? So
Yeah.
you would just have to like figure out your possible nucleophile atoms, electrophile atoms, and choose the best combination that leads to the most stable ring.
So you should choose when you're doing like the intramolecular ones, you should choose like your like would you recommend like for like numbering them, my like number one carbon is my nucleophile?
Yeah, you can number it like that. Other people number it the other way. Like they number one the carbon, no carbon like that. Two, three, four, five. It does the same thing. It tells you how many atoms will be in the ring, how many members you have in the ring. But when you number it that way, just make sure to keep everything consistent. Like if this is one, this would have to be one with the turbudo because that will help you attach the copy and paste decorations like that. Right? So you can number it from the nucleophile to the electrophile, or you can number it from the electrophile to the nucleophile. You get the same product as long as you're consistent with the decorations. Right? But I like starting my number one atom, the nucleophile, and ending with the electrophile.
Hmm.
Because the nucleophile goes towards the electrophile in these reactions. Right? The numbering system here is not like official. It's just a tool to help you predict the product quickly to show you how many members will be in the ring.
Yeah.
Right? Okay. Um, Now, on our second session, we'll go over um, the rest of chapter 17, 18 reactions, right? But we went over, well, actually, we'll go over micro addition and Robinson annihilation to finish up the big three reactions for chapter 18. And then we'll do some synthesis problems from cumulative chapter, like midterm 1, 2, and 3, alkene, alkyne, benzene reaction synthesis as well. But I want to finish the big three for chapter 18. We're done with aldol
Hmm.
condensation and dehydration already.
Okay.
Okay. Um, any other questions, Hannah?
No.
Okay, that's good. I'll see you tomorrow for our session at 12 to 1 p.m.
Yeah.
That's good.
Okay. See you tomorrow. Thank you.
Of course, Hannah. I'll see you.
Okay, bye.
Bye.